Hi, it is William with Dorse and Company. Lately, we have been receiving requests regarding compliance with the 2015 Washington State Energy Code, in particular Section C403.2.11.3, which prompted the creation of this video. Several slides in this presentation have been taken from presentations hosted by Greenheck Fan Corporation. In this video, we will cover the basics of fan efficiency, which will lead into the actual code requirements and what fan efficiency grades really are and how they are defined. Next, we will discuss which fan types are most impacted by the code, along with where the industry is already moving and what will be replacing fan efficiency grades in the future. We will conclude the video with what Greenheck is currently doing to make selecting compliant fans even easier, along with a demonstration on how to make sure our fans are compliant. Starting with the basics of fan efficiency, fans have several areas of inefficiencies, especially belt-driven fans. We have power input into the motor and an output in the form of airflow and pressure. The efficiencies are in the motor, the drive assembly, bearings, and finally the aerodynamic losses. Here is another way of showing the same information along with relatively standard losses. Fan efficiency lies in the aerodynamic losses. This is based on how efficiently the air contacts the blades. Fan efficiency is defined similar to any other efficiency, power output divided by power input. For a fan, the output is CFM in pressure. The input is brake horsepower. We will cover these formulas in more detail later on in this video. They're a little more complicated than what is shown here. Now that we have covered some of the basics of fan efficiency, what does the code say? It says all fan systems must have a fan efficiency grade of 67 or greater and must operate within 15% of the peak total efficiency. There are a few key exceptions, including fans less than or equal to 5 horsepower, packaged equipment, powered wall and roof ventilators, and finally emergency fans. There is a stretch code under C406.2.3 that says all standalone fans for supply, return, and exhaust that are over 1 horsepower must have an FEG of 71 or greater. In addition, the fan must now operate within 10% of either the maximum total efficiency of the fan or the static efficiency of the fan. Since this is a stretch code for higher performance buildings, we won't focus on this in this presentation, but it does exist. Essentially, it is just making the code a little stricter by narrowing the selection range and forcing us into a higher FEG requirement. The biggest hurdle here will be that they don't list any exceptions in the code under this section. So now that we know what the code says, what exactly are fan efficiency grades and how are they defined? It relates impeller size to peak total efficiency. It is based on a set of curves, and depending on where the impeller size and peak total efficiency falls between these curves, it defines the fan efficiency grade. The next slide will break it down better. I do want to emphasize that it is not an indicator of operating efficiency or performance. The FEG is merely an indicator of peak total efficiency for that fan model and size. Because of this, the code requires to select fans within 15% of peak total efficiency. If the code didn't have this, it would be relatively useless from an application standpoint. This is how an FEG or fan efficiency grade is determined. It isn't calculated to a specific number, it falls within a group. With peak total efficiency on the y-axis and fan impeller diameter on the x-axis, a fan can be given a fan efficiency grade without moving any air. Seems kind of worthless, doesn't it? For example, with a 30-inch impeller and a peak total efficiency of 72%, the fan efficiency grade 75 is assigned. The same FEG can be applied to a 12-inch impeller with a peak total efficiency of 64%. Again, completely independent of actual operating performance. The points within peak requirement is what dictates the actual operating efficiency. This chart is a great indicator on what impeller types result in higher fan efficiency grades. Forward curved blowers are the lowest typically, with airfoil centrifugal wheels being the highest. Backward inclined wheels tend to meet the higher static pressure requirements and aren't the least or most efficient wheel type. The static and total efficiency formulas are similar to what we covered earlier. Substitute out the pressure to either static or total pressure, and you have either static efficiency or total efficiency. The important part to note here is that the total pressure is a sum of the static pressure and the velocity pressure, and will always be higher than your static pressure. You will see on the chart here the peak static pressure is roughly 72%, and the peak total pressure is closer to 80%. We can actually break the fan curve into three major regions. The surge area is on the left of the fan curve. It is in red, and you shall not or should not select fans in this area. The bottom half of the fan curve is the least efficient and the loudest part of the fan curve. As you move up the fan curve, the efficiency increases and the sound decreases. This is an extreme example, but a real example of a high volume, low pressure fan selection. For 40,000 CFM at a quarter inch of static pressure in a non-ducted application, the prop fan is the right fan for the job. The 54-inch prop fan I am showing here has a relatively low FEG value, but a similar prop fan in a tubular housing with a higher FEG value actually consumes more power. And the vane axial, designed for much higher pressures, isn't much better. You can see the ratio of first cost on the right hand side. You would never see the vane axial pay for itself in energy savings for this example. I included the airfoil centrifugal fans just because their FEG value is so high. The similar sized impeller uses almost twice the power. And in order to get the power down, you'd need a much larger blower wheel. I could have selected a sidewall prop fan with a higher FEG value, but the power consumed isn't necessarily any lower. Again, the FEG value is based on the peak efficiency, not the actual operating efficiency. The total efficiency in this case isn't a very good indicator of the actual power being consumed. Essentially, following this code requirement to the T would replace a fan like this with one like this, and that does not make much sense. This is a slide to point out that FEGs are not a tool for fan selection. This chart shows information on a group of fans, single wide airfoil centrifugals, that might be considered for an application. All 6 of the fan sizes shown can be used to meet the requirement of 15,000 CFM at 4 inches of pressure. The available sizes are shown from smallest to largest. The small fans are higher speed, and you can see they're bumped into higher classes. The operating power varies considerably, the smallest fan using twice the power as a larger fan. The actual fan static efficiency is shown varying from 38% to 78%. Actual total efficiency, as expected, is higher, ranging from 55 to 83%. We can look at the peak static efficiency attainable for each size, and finally the peak total efficiency attainable for each size. Now notice the FEG values for each size, they are all the same. So again, FEGs are not a tool for making a fan selection. They simply classify the fan based on its peak total efficiency or its potential to be used as an efficient fan. Looking at the same fan sizes and models, you'll see that the cost varies based on size and fan class. By looking at the total cost of ownership over a 5-year period, we can see which fan makes the more sense over the long term. It is a balance between first cost and operating horsepower. These total costs of ownership are only looking at power consumption, not actual fan maintenance. But for this example, we can assume the maintenance costs would be relatively similar. And the size 33 is the fan you would inevitably want because the total cost of ownership over 5 years is lower than any other selection available. Now that we know the FEG isn't a great indicator of efficiency, let's look at fans that are most impacted. With powered roof and wall ventilators exempt, the 2 biggest categories left are inline fans and scrolled centrifugal. This will move your selections from the most first cost-effective square inline centrifugal fan like the BSQ shown on the left to a mixed flow wheel in the middle and right. The middle fan is an EQB and it's much closer in cost to the BSQ, but it's also more efficient. If you need higher pressures, more than 3 inches, or higher airflows above 26,000 CFM or so, or if you're going to be mounting the fan outdoors, you're going to want to go with the QEI. But for all other applications, most of which the BSQ is used for, the EQB would be a great solution. Scrolled centrifugal fans are impacted as well, but typically there would be a selection that will meet the FEG code requirements without changing the model. You just need to select a different size. If you don't know what a mixed flow wheel is, you probably know what an axial wheel and a centrifugal wheel are. The mixed flow wheel is a hybrid of the two and orients the air at 45 degrees versus 0 or 90. Axials can move a lot of air because it's passed through, but they can't achieve very high statics. Centrifugals do 290 bends. They can achieve really high statics, but they can't move quite as much air. The mixed flow orients it at 45, so you can balance between the two. Oftentimes you can select a mixed flow fan at lower noise, lower horsepower, and a smaller fan size than an inline centrifugal. Now that we understand the limitations of FEG, where is the industry already going? There is already a replacement in the works, and it is called the Fan Energy Index. It will be the calculation of the baseline fan electrical input power, or FEP, over the actual FEP. It varies based on the operating point for a given fan and is independent of fan type. So now exemptions won't need to be made for powered roof and wall ventilators, and it will allow all fans to be judged according to where they should be operating against the baseline. The requirement would become as simple as the FEI must be greater than or equal to 1.0, or as we were mentioning earlier, for those stretch goals, maybe it would be 1.2. Here's an example of what a chart in a catalog might look like, where all of the highlighted sections in gray are greater than, that has an FEI greater than or equal to 1.0. This is from the AMCA white paper on fan efficiency, or fan energy index. Here's another chart of maybe what would show up in CAPS or ECAPS, and in this case everything highlighted in gray again has an FEI greater than or equal to 1. Here's maybe what a high efficiency fan curve might look like, where you're able to select the fan all the way up to its max speed. And you'll see here it's ISO efficiency plots that you can select between. And here's a lower efficiency fan where you're going to have this max speed be lower than the actual max speed of the fan. Here's maybe an adjustable pitch axial fan. Instead of a whole zone, you have an isolated area. So inevitably you might now understand what FEGs are, but that's not going to do you much good if you don't know how to select a fan and where you can go to make sure your fans are compliant. Well, if you're familiar with Greenheck CAPS, Computer Aided Product Selection, CAPS 4.22 should have the majority of impacted fans updated with FEGs and points within peak. Predominantly these fans that fall into the centrifugal and vane axial category, the ones that are overall most impacted, such as those QEIs we mentioned earlier, and the centrifugal scrolled wheel. ECAPS, though, is constantly updating with the newest data, and it should have the data you need for most fans. If you're early in the selection process, I would recommend starting in ECAPS, where you can customize the schedule with this data. We'll cover that shortly. Now let's walk through a couple selections and show you how to adjust column headers and make your job easier selecting fans compliant both in ECAPS and in ECAPS. If you're not familiar with ECAPS, it's completely online. You don't even technically need a login to select a fan. If you want to save your selections or export any submittal data or schedules, you will need to log in. If you know your CAPS login information, it is the same. The benefit is you have completely customizable column headings in both the selection process and in your scheduling process. And as I've said, it contains the most up-to-date data. At this time though, they only have fans and louvers, but in the future they will add more products, so stay tuned. So here we are in ECAPS. I'm going to go through some things in ECAPS. I'm not going to do a full demonstration. If you want a few more details, you can click on this link, and GreenHex prepared a video for that. But for what we need here, I'm just going to walk through how to make sure your selections are compliant. And I'm going to start with inline fans. ECAPS will work on mobile devices. It won't work on your phones, but it can work on tablets. You just need internet access. So here I'll run a selection at, let's say, 5,000 CFM at 1.5 inches. And let's do 2,300 feet. And then you could just tab over, and then it will force the selection to go. So here, if you need special requirements, you can put them in. More advanced inputs, if you're a little bit more familiar with CAPS, this will make sense. Many of them will impact what the performance of the fan is, so you can help compensate for inlet and outlet conditions, guards, dampers, belt tubes, that kind of thing. So here we are with 46 fans available. And what we want to do is make sure we're going to comply with energy code. So if you click on this little gear next to any one of these columns, you can hit column chooser. Then simply scroll down to the data you need. So points within peak, that's one data column you'll want. And fan efficiency grades, I probably already went by it, didn't I? Oh, there it is. Fan efficiency grades, and just hit apply. So here we go. Fan efficiency grades, points within peak. You'll see this BSQ, your FEG is only 53. That's why I was stating earlier, you might want to look more towards the EQB because you'll see the FEG is closer to 75. So if you just type in 67, enter, it'll filter out those 46 fans down to only 22 fans. Now you know all of your FEG are at least greater than 67 or greater. And this column you'll see less than or equal to here in gray. It might be hard to see in the video, but if you type in 15, enter, now again we're all 22 we're within 15%, so we were okay, but it will filter those out too. We're still at 22. So if you click on the fan model, you'll see a little bit more information here. A little bit more information about the fan, some sizes, drawings available, AMCA, sound and air performance, all of that. Here's your fan curve, your operating conditions, and your min-max fan curve. Here you go, max fan speed, min fan speed, dimensions, drawings, all of that. If you want to customize it, you can tag it and put it into your fan schedule, and you can select different horsepowers and all of that here as well. Let's say you want a 5 horsepower fan. There's another part of the energy code that you might want to look at though before you go from a 2 to a 5 horsepower fan. So then you can click schedule, and then here in the schedule you can go look, and you've got your EQB. So well, now you need to schedule that data, right? That's the important part. So again, column chooser, and I don't believe GreenHex quite has all of that data in it. Looks like they have the FEG and points within peak. It looks like they've updated that. So then you can click apply, and then there you go. Your FEG 75, points within peak, you're spot on. You can add your notes in down here, and then you can type in your notes here. Notes, I'm just throwing them in 449. Oh, excuse me. And there you go. So you can save your job. You can keep adding more fans and louvers to it. You can download your schedule, cut sheets, your caps file, all of that. You can even email it right out of here. Here you can, again, save the job, and then when you go to share it, you can share it with your rep, like us. You can send it to Scott or myself, and we can go through the selection and make sure everything looks good in ECAPS. Key thing to remember, once you take it from ECAPS and bring it into CAPS, then it's in CAPS. So ECAPS is great for the early selections and the rough detail, but then when you really need to fine tune it, you got to go into CAPS. You can talk with us about doing that, but hopefully you can get everything you need right out of here. Their equipment schedule is great. You can add your own as well, your own notes. So I'm going to go back, and GreenHeck has added louvers. They will be expanding ECAPS as well into the future. But if we get a lot of requests for budget pricing as well. So, and you might not have noticed on that last fan, but there is a column for budget pricing. That's another nice feature about ECAPS. Our elevation was saved. You'll see that here. And we're still in the same browsing session, so FEG and points within peak are saved as well. But your filters have cleared out, so you'll still need to type in 67 and 15, and now we're down to 16 matching records. So here you'll see your budget price for the fan and your operating costs per year. So ECAPS is ranking your fans based on your costs, your horsepower, and your noise. Those are the key features that are being ranked here. So if you follow this rank, these fans should be a great selection for you to go with, the top few. I wouldn't, if I were you, I would look at the top few of them. I wouldn't just pick the top one automatically. Just make sure you're happy with where it's operating, your horsepower, all of that. Now, something you'll note, you might have seen these, that they are shown in more detail in the ECAPS tutorial, but ECAPS will actually warn you when you aren't meeting either your performance or you're close to not meeting your performance. So you'll see here operating volume is below the required volume by 4.7%, and we'll see 0.1%. There's a few different warnings you might see in here. All of them are based on volumes not being met. But another nice thing, and again I said I wasn't going to make this in ECAPS tutorial, but if you're looking for system effect, you can also look at that here in ECAPS. So let's say we're looking at a roof exhaust fan. Well, we're not going to have an outlet condition because it's going to be exhausted right out here. This is a downblast fan. So, but let's look at our inlet condition. Maybe we've got a really nasty elbow right at the inlet, and we can look at how much volume is lost, power increase, RPM increase, all of that right here. And you can look at the assumptions here. But let's say we have a blower and we do have inlet and outlet conditions. You can look at various elbows. You can add a little bit more ductwork on there. You can look at a bunch of different situations and how it affects your overall performance of the fan. And I think that will wrap up our ECAPS portion of this tutorial, and now we'll move into CAPS. So here we are in CAPS. Hopefully it looks familiar to you. If not, well, feel free to contact us and ask us a bunch of questions. There are some good videos that we've been publishing online that can kind of walk through some of this stuff too. So before I select a fan model, I will show you one feature that you'll want to look at in one setting. So when you go and click on updates and settings, go to your job template, and then under preferences, you'll see show points within peak total efficiency. It may or may not automatically show up on most fans. I've found that it does more times than not, but that's one place to make it easier for it to show up every single time. So now we'll click on the EQB, and we'll hit enter. We'll pull up a quick selection here. I'll just name it Mark 1. Let's run it at 5,000. I think that's what I did earlier, 1.5 inches or so. And click show available sizes. So here several sizes will populate, and you'll see points within peak total efficiency. If it's not here, you'll want to click on customize grid, and it's actually not visible here because the EQB is not in fully loaded in ECAPS yet. So I just want to show you that. We'll go to the QEI though, which is in the CVI division versus fan event, minor detail. But this data will be loaded in here. This will give us a few more options. You'll see fan class 1 and 2 over here. It's also shown here. But here you'll see points within peak total efficiency and FEG. If you don't, you can click customize grid and click show points within peak total efficiency, and then you'll be able to make sure you are compliant. So here 75 points within peak 8. Look at the fan curve. We're a little bit, like I said, bottom 2/3. We are still okay with this fan wheel. So because we meet the FEG of 67 or greater, and we're less than 15% off of peak total efficiency. So we're still in a good spot. So that's all I needed to really show you in ECAPS to comply with the energy code. But as always, if you ever have any questions, please feel free to contact us. All right, thank you.